put it on a piece of paper, like a graph paper. That's the way I like to equate it. Take a piece of graph paper, and you're going to assign it a number. They call this a quantization table. Now, with this graph paper, you'll notice that there's, between, I think it's negative 127 to a positive 127, which is the next portion of this, and each space is equal. Now, when you look at the pulses, you're going to find out that these pulses most of the time are going to fit on that graph paper, but there's ones that are going to fit in between it. Now, where does that fall into place? Well, you got these little issues called quantization errors when they fall into it. Now, let me go to my settings. And I want to make my mouse just a tad bit bigger. I just discovered this too. Mouse. Let's see here. Cursor size. Let's go to this. There you go. It's a tad bit too big. All right, so you see this place in between the two lines. Well, that's a quantization error. Now, you're going to do something called rounding, which is you round up or you round down. Now, everybody knows that when you hit 5, you're going to go up. If you hit 4 and less, you're going to go down. So that's the quantization error. Now, we take a look at the whole graph paper of it being equally spaced, and we call that uniform quantizing. So the next portion of this is how do we get around the quantization errors? So when you take a look at the errors, come on, there we go. What they figured out is if we squash the lines together like you see here, the issues that we have is we're eliminating some of what. Yeah, I see that. How do we get 256? I'm sure someone was going to ask that question. I'm getting there. Let me explain the quantization errors first. By squashing the lines together and spreading them apart at the top, it becomes non-uniform. But what they figured out is if we can squish as many lines together as possible where the normal voice is, when you have people that are really high-pitched in their voices or really low-pitched in their voices, then what happens is you'll have the quantization errors in them, but the people that are in that general area of where all the squashed lines are, you don't have quantization errors. Still have them, but you don't have it as many of them. Now, errors are considered distortion, but you got to have a lot of them to really make a difference on it. But what they found out is by eliminating most of the errors, you don't have this issue when you reproduce it on the dissonant. Now, Sir McCusser, came up with the 127. How do we get 127 at the top here? You can see 127 here and 127. Well, if you add those two together, what do you get? You get 254. Well, I'm going to go do some drawing here. Hopefully. So, first of all, 127 plus
Can you hear me, Mr. Mayor?
Oh, God! Oh! Who was that?
Yeah, he can hear you, Matt Sergeant.
Yeah.
That's Sergeant Sackett. Hey, man, you've got some echo.
Do I?
Yeah.
Sorry. Good grief, man.
I didn't mean to blow your ears off. I'm sorry about that.
No, I have to readjust. How do I have an echo? All right, let me go to my...
I think it's because you're also recording right now, sir.
That's a possibility.
Yeah, if you want, you can turn yours off. You're recording off. I'm definitely recording you as well.
Okay, well then let me stop it
Well,
then.
then let me stop it then.
Just make sure that you send me everything, okay?
Send me everything.
Yes,
okay?
sir.
Thank you.
Thank you.
Alright, so,
So,
127, 127, what do you come up with?
What do you come up with?
254.
4.
Alright?
All right.
So, we have,
we have.
let me try this on the other part of this. 1,
1,
2,
2,
4,
4,
8.
8.
What's next? 16?
What's next? 16.
Start to see a trend here. 32.
32.
What's next? 64.
64.
And then, lastly but not leastly, you have what? 128.
What? 128.
Why don't you add all these together, and what do you come up with?
What do you come up with?
Right?
Right?
No.
No.
Scrap that number.
Scrap that number.
255.
255.
Well, wait a minute.
Wait a minute.
We got an issue here, don't
We got an
we?
issue here, don't we?
No, not quantization
No,
error.
not quantization error.
When we make an AC
When we
signal,
make an AC signal,
this is positive,
this is positive,
this is negative.
this is negative.
This last number
This
here
last number here
tells us whether
tells
we
us
are
whether we
positive
are positive
or negative.
or negative.
So, when you add
when you
64 all the way down to the 1, you should get about 254.
254.
When you add
When
this
you add this
in here, you'll get that last.
You'll get that last.
That didn't sound right, did
That
it?
didn't sound right, did it?
Let's see here. 128. Yeah, you'll get the 250. 255.
255.
This last part right here
Last part right
identifies
here identifies
by doing either a
by
plus
doing
or a
either
minus.
a plus or a minus.
So you're either going to be
So
here
you're
or
either
here
gonna
on the
be here or here
quantization
on the
table.
quantization table.
So far, so good?
So far, so good?
Yes, sir.
Oh, crap.
Good to go.
Oh, crap.
Who was that?
Who was that?
Staff Sergeant Fairfield.
Okay.
Okay.
That could be the reason why.
Could be the reason
I gotta bring you down a little bit.
Bring you down
All
a
right.
little bit. All right.
So you have,
So you have
the next one, let's
one,
see here,
let's see here.
encoding.
Encoding.
And this is where that,
And this is where that
plus
plus
and minus
and
come into
minus
play. Is that
come into
8
play.
bits?
Is that
It's,
8 bits is
the 128
the
portion
128 portion
gives us that
gives us that
plus or minus the
plus
negative
or
1,
minus the negative
plus
1 plus
127 or
127
minus
or
127.
minus 127.
So those are the three
So those are
steps
the three
that we
steps
look
that
at
we
when
look
we
at
deal
when we
with
deal
the
with
last one,
the last
encoding.
one,
So you
encoding.
have
So you
all
have
these numbers,
all these numbers
like I showed you back
like I showed
on
you back on
Krita here. You got
Krita here.
1,
You got 1,
1,
1,
2,
2,
3,
3,
4,
4,
5,
5,
6,
6,
7,
7,
8. There's your 8-bit
There's
code
your 8-bit code
when we're looking at
when we're looking at
encoding.
encoding.
So you can see the
So you can
last
see
number
the last
right
number right here
tells us
tells us
whether or not we
whether or
are
not we are
above the line, the zero line, or below the zero line.
the zero line.
So that
So
128
that 128
is where we
is
see the plus
where
or
we
minus
see
at.
the plus or minus at.
Any questions on that?
Any questions on that?
Negative, positive,
Negative, positive, split,
Sergeant Fairfield?
No, sir.
Sergeant Fairfield?
Okay.
Okay.
Swartz is
Swartz
typing
is
in.
typing
So he's
in.
got a question.
So he's got a
So
question.
Sergeant meets,
So
so
Sergeant
we'll be
meets,
there for
so
a sec.
we'll be there for a sec.
Negative logic?
Negative logic?
I'm not the engineer on that one. Can you advise there, Sergeant Sackett? They're asking if this would be negative logic. I thought negative logic would be as if you're in the negative side of the field all the time, and zero would be your plus. You want to enlighten us there, Sergeant Sackett? He's vacated the farm.
Yeah, I don't know if he stepped away or not.
All right. Well, when everything else fails, right? Good grief, what's going on here? Figures. Well, there you go. This little chart right here. It's positive logic. Where's the negative logic? It's opposite of it. So in other words, if true was a 1, false is a low, then the opposite of that. Yeah, you could actually say that would be a negative logic there. Ding ding. Crazy stuff, ain't it? So does this make PCM a little bit easier to understand?
It's a
Okay.
bit more clear, sir.
All right. Where is it that you're having issues with? Yeah, that didn't sound confident there.
It's just going to be memorization for me, sir.
Well, how many steps are in that PCM?
3.
And what are they?
Sample, encode, and quantize.
Okay. So what is the errors called? In other words, if I have to round up or round down, what's the errors called?
Good question.
Not uniform, it's called quantization errors. Because you're in the quantizing portion. Remember, when you take a sample and you put it on that chart, here, let me go back to this again. When you put that back on the chart, and you'll notice that you can see where my crosshairs are. You see that space where it's fitting in between what looks to be like 3 and 4? Well, that's an error. And because of it, you also have to understand that it's going to create some distortion when you do some playback on it. Now, you also take a look at the more you sample, in other words, if you go from 8,000 times a second to 16,000 times a second to, as you keep doubling, the better the reproduction is, because now you're going to clear out most of that distortion area and keep it down a little bit easier, because everything's in that little non-uniform quantizing. But nowadays, I'm going to show you this program I have called Audacity. Now, I'm not sure if you guys have ever used Audacity, but I'm going to bring something up here just to give you an idea. The more the sample, the better the quality. So, let's go File, Import, Audio. You gotta be kidding me. PC. Let's go Music. Nope, wrong.
Nope, wrong.
Here we go.
Here we go.
I'm just going to pick one.
I'm just going to pick one.
Oops.
Oops.
Yeah.
Yeah.
Now, for those of you who know what Audacity
is,
do the MP3s.
do the MP3s.
Let's not do the MP3s. Let's do the WAV files. As you can see, I'm a big. Yeah. Okay. All right. There's a file. All right. So this is about as representative as you can get for an analog file form. So when I come up here to, I gotta remember. Cancel that. I gotta find it first. Kind of hard to read through this. Oh, wait a minute. There it is. I forgot. There it is. Export as an MP3. All right. When it pulls this up, hopefully you guys can see this. Down here, here's your quality. You'll notice it says extreme, 220 to 260. Yeah, that's pretty crazy. Insane is 300K. If I get it down to medium, that's 145. So you can see that there are differences when we sample this. And this is what this particular program is going to do, is sampling it at a crazy amount. Okay, somebody's trying to chime in. Everybody okay? But it gives you an idea as to when you exceed the Sarbudo.
Your mic's on, Sarbudo.
Crazy.
So, wow. So as you can see, that particular program can save it in a ridiculous amount of sample rate. When you get it reproduced, it's going to sound so much better. Now, why do we do 8,000 times a second? Well, you remember back in, what I think it was in block 2 there, Sergeant McCusker? They use PCM for that, don't they? And
Yes, sir.
It's very basic, don't they? So,
Correct.
So
you don't need a stereo system full of, sample rates ridiculous. We would just want to keep it simple because we're just trying to do COM, and that's the reason why we use this PCM for all of our digital radios nowadays. Now, there's probably some out there that does it a little bit better than others, but this is the basic concept and why we need to know PCM in a residual sense. Any other questions out there? On PCM. Questions? Okay. I might be in a gaming chair, but good grief. Okay. Who's next?
I know we had questions, or somebody had a question on CDI.
Okay.
Timing.
Okay.
Ah, yes.
Ah, yes.
All right.
All right.
CDI, what do you want to know about it?
What do you
All of
want
it?
to know about it? All of it?
Part of it?
Part of it?
Clarification, what?
Clarification, what?
Let's go over all of it for safety's sake.
CDI. Okay,
CDI.
I'm on the
Okay,
slideshow
I'm
here.
on the slideshow.
The big thing is the CDI is one of those things, if you were to look it up, first of all, and I'm kid you not, go to Google, you look it up, you're not going to find CDI anywhere. However, you will see something called Manchester diphase, which is a derivative of CDI.
Now,
let's take a look at what we have on the slideshow. It says it uses transitions from bottom to top and top to bottom. We look at logic ones. Now, logic ones are only one of those transitions. With logic zeros, there are two. Now, this little statement right here, CDI is self-clocking. Well, let me explain this. When we go to this particular waveform right here, you can see that we've got a clock pulse down here, and this one up and down, you'll notice that it is constant. You're going to have clock pulses throughout your multiplexer. That's the way everything is working about timing. So when you take a look at this zero up here, you will see you have two transitions. Now, let me explain something about how we look at these two transitions. With general speaking, we always start at that zero line and go into the positive side of the house. That's the way it is in electronics. So if you're dealing with a sine wave, you're always going to start with a positive wave and then go to a negative wave. That's a general consensus on where everything starts. So in this case, we got from 0 to 5 volts. So we start at the 0 volts, and for a logic of 0, you've got two transitions. So here's the first transition, here's the second transition. So there's two within that clock cycle right here. Now, I want to point to you this up here. What's it called? Data. So in other words, I'm trying to get something to get to the distant end. This is my data. This is what CDI is going to do with that data, and it's going to do it within the clock pulse. Now, I do have to say there is something about CDI that is a little unusual. As long as you get two transitions within this clock cycle, you're good to go. Now, most of the time it will hit somewhere along those lines of when the clock cycle goes up and then the clock cycle comes down, it will hit those. But it's notorious sometimes for hitting that in between the ups and downs. But as long as it gets, in this case, a 0, as long as you get two transitions in it, you're fine. A lot of people miss the fact that there's always clock pulses that you have to have on the starting end, and on the distant end, it's going to put it back together. And the distant end actually has a clock cycle going, an oscillator, in making sure all the timing is good. If not, everything falls apart. What's nice about not having to do this so-called self-clocking is I don't have to send this clock cycle down to the other end. All I have to do is send the data. So it makes it more easier to send it from point A to point B. Now, not everything is going to work with CDI. Most of the time, it's some type of NRZ. As far as isochronous is concerned, yeah, that's another issue, which is, async, sync, and ISO. So with this in mind, the clock cycles, when you're dealing with async or sync, this is what we go by. This is the data at the top that we're sending to the distant end. Any questions on that for CDI? Does that kind of clear it up for you there, Sergeant Fairfield? Fairfield?
Thank you.
Any other questions on, let's just say, the clock cycles or anything else along those lines? Good. Okay, you're going to have to redo that, Sergeant Airman Schwartz. That BRZ. Can you explain that one a little bit more? Oh, NRZ? No, well, that's what I was thinking. Oh my goodness.
Yeah, I walked into that.
Yeah, you did. So you want to know about zero suppression. Did I get that right? Okay. Let's go back and talk a little bit about zero suppression. All right. So bipolar with zero suppression. Now I'm going to tell you something now. This particular format is a little strange. You have to look it up in the NSM because it deals with the couple of where does that bit violation fall into. The format, bipolar with zero suppression, deals with, okay, bipolar. One's going on top side, in other words, the plus side, and the next side is going to be down at the bottom side. That's that bipolar. So you're flip-flopping between the zero line, one negative, one positive. So with a bit violation, the whole idea behind a bit violation is if I end up with a data of 1 and I flip it to the up position, another data 1 comes in, I flip it into the low position. Realistically, the next piece of data that comes in should be a positive. Well, with bit violations, the idea behind that is I tell the dissonant, hey, if I have a succession of, let's just say, 4 zeros, that fifth zero, I need to throw a bit violation. So if I was supposed to go high and end up throwing low, the distant computer then knows, I had one too many zeros. That's the whole logic behind the idea of bipolar with zero suppression. That zero is where it keys into, and that's where it throws the bit violation. So let's take a look at this particular one right here. In this case, it looks like we got a particular code of a 4. In this case, you're telling the computer on the distance end that the fourth zero you need, or the third zero you need to throw, if it's a bit, let's try this again. If the fourth zero is, I get it. If I throw 3 zeros and the fourth one is another 0, I got to throw a bit violation there. That's what it's talking about. So as you notice that here's a 1, here's another 1. Okay, if I was to throw another data of 1, I should have this going on the up side, not the 0 side. Because bit violations are going to look back down the line and say, hey, my last 1 in this case was a -5, so I'm going to emulate it to show the distant end. I got a problem here. I got 1 too many zeros. And what that does to the distant end, it realizes that and goes, okay, I just had 3 zeros, the fourth one is 0, and he threw me a bit violation. Bam, I'm back in time now. That's how that works. Now, there's different formats out there, and it is in the NSM tech manual that shows that some of them are you're throwing that bit violation at 4, and then there's some that throw the bit violation at 8. So you've got to look at that as to see where that bit violation is going to happen. Now, if we were to throw it on the other end and you said, well, gee, this one was here, and this data was a 0, or excuse me, a -5, this is a +5, then this one should be, because it's a bit violation, would be in a +5. Does that make it easier for you? Hey, let me know now. Need to know. Kinda? Okay. Help me out here. Where are you struggling at? Holy cow, everybody's writing. So what is
That's just
slide
the
saying
example
about?
that the book gives. That doesn't
Okay.
necessarily mean that's the right thing.
Yeah, there's different formats out there that if there are 4 zeros in a row, the 5th zero is where they're going to throw a bit violation. It depends on how they write it. If you were to go online, and again, when you take a look at this, is sometimes it'll throw it, if you say a BZ4, you can have bit violations depending on how that's written. It could be throwing it on the 4th, or it could be throwing it on the 5th. Good point there, because 8BZS, there are many variations. That's very true. In fact, let me see if I can find it on Google for you. And I'll just try it. AMI code, alternate mark inversion is the same thing as bipolar with zero suppression. Oh. There's a better way of writing it. Nope. I should have kept that website. Here we go. This one you can see in the NSM, this B8ZS. This one is saying looks like on the 8th one, it'll throw it. Yes, bit framing, gotta love it. But there's several different variations that can come with that. That is true about case by case. So the question is, good point. And that has, now you're on an upper level of learning. At B8ZS in T1 trunks, you're on a different scale of learning there. So let's just keep it simple and say, well, what are the 3 self-clocking modes for sibling formats? What are they? Can anybody tell me? CDI is one of them. What's the other 2? RZ Polar and RZ bipolar with zero suppression. So those are the three that we look at. Now, why do we concern ourselves with those three? Because you don't have to send the clock to the distant end. Even though it's clocked at the multiplexer, the distant multiplexer is going to sync everything up. Any other questions out there? Not necessarily. For example, if it says 8, depending on how it's written, it could fall on the 8th zero or it could fall on the 9th zero. Same with the number 4. It could fall on the 4 zero or the 5th zero. That's what that format is talking about. And I think the NSM is, one of them says that you will throw the bit violation on the 4th one. The other one says it'll be on the 9th one. Sergeant McCusker, pull up the tech order and take a look at CDI. It should give you alternate mark inversion as the two different codes.
You're talking about the tech manual for the NSM?
That is correct, sir. I don't have those with me. If you would, please. And just write it in the chat. That'll help.
Yeah, no problem, sir.
Thank you.
Are you just looking for the ports?
It should be in the CDI or alternate mark inversion portion of those ports. It'll come up with like BZ8 something other, and then it'll have like one of them has a 4.
I found one of them.
Okay, great. You're on the right path then. Now, there you go. AMI or B8ZS, and that one will throw, if I'm not mistaken, will throw the 0 or the bit violation at the 9th zero. There's one in there that has a 4 on it, and that one throws it at the 4. But you can see where it says B8ZS. There's others that I think it's B4HD. It's been a while since I looked into it.
It's a 3.
It's a 3? Okay. That's throwing it on the 3rd zero. Oh, you're going to have to write that one down. I don't want to. Okay, HDB3. So at the 4th zero, AMI or HD3. Let me verify that.
Yeah, they're under the T1E1 group ports.
HDB3, HD. I got that written. Modified code. Yep. 3rd zero. If it sees 3 zeros in a row, the 4th one will be the bit violation. Let me write the B8ZS. Okay, this one throws it at the 8th zero. And like Sergeant Sackett said, it's a T1 line. So you can see how it's different and where they throw the zeros. It depends on how that code is written to, make it self-clocking. Any other questions out there? I gotta go back up there. Okay. By the way, Sergeant McCusker, ever since I quit recording, I take it the echo is off?
It's still there, but it's fine.
Okay. Let me see if I've got something else that's, oh, you know what? How about now? Check 1, 2.
Still there.
Can you hear me?
Okay. Sure can there, Sergeant Sackett.
Hey, so Sergeant Pollard, Sergeant McCormick, and I figured it out. Your video has an audio feed with it, and you're coming through in the voice channel. The microphone that you're using for your voice channel sounds great, but the one coming with your audio sounds a little worse.
Okay.
So we've been just muting the video and listening in voice chat.
Okay. I'm so blind. All right. So, in regards to the tisser, I note that the pre-selector is turned to the front panel control, but what's it tuned to? Good question. All right. So when you're doing the tisser, you have, let me go to this here real quick. Let me get out of this particular one. Click up here. As soon as I can find my Block 7 stuff. Where are you, slides? Is it 4 Charlie where the slides are, Sergeant McCusker?
I'm pulling them up now, sir.
I'll take a gander. Signal flow. Okay, here we go. Bingo. Okay, so everybody can see this. All right. When you're doing the pre-selector, you see this right here in the A1, A2 microwave LRU. How do you see it? There's the microwave LRU. Here's the dotted lines. That pre-selector has to be what your receive frequency is, because here's your receive encoder here that's going to come up and give that oscillator another frequency so you can mix the receive frequency with it to get whatever you need coming out. So that pre-selector, and you've seen it in a couple other radios too, if I'm not mistaken, Block 2 and the PRIC 113 shows you a pre-selector in there, and then you have one that's overall selectivity. So if you wanted to come with that concept, there's a pre-selector, so it's got to be set in the receive frequency area. Now, it's going to be broad. All it is, it's a filter. It's a broad filter, but where everything becomes a overall selectivity happens in the control and distribution LRU, right around the bandpass filter here. So that bandpass filter is centered on 70 megahertz. How is it centered on 70 megahertz and not the receive frequency? Remember back here, when you had that oscillator, it's going to generate 4 frequencies. You got the sum, the difference, the 2 originals, which is one will be the operating frequency. The other one will be the oscillator frequency that the encoder is producing to simulate a frequency to get the 70 megahertz out. When it hits the bandpass filter, that's where overall selectivity happens. So pre-selective filter has to be set on a receive frequency. Now, when you look at the tisser, what's on top? when you're doing those frequency dials. Oh, gee, the frequency dials is the transmitter one. So they're flip-flop. So always remember your receive is on the bottom. Take a look at the bottom left, I think, on your RF module, and those two have to line up. Now, the adjustment for that is again, it's a broad range. So you can be kind of off center a little bit and still be able to get that frequency out that you need. So the idea is I need to weed out all the other frequencies, but I just need to center on just receive frequencies. The other question too is, how many frequencies are you given for the TISR? 2. What are they? Transmit frequency, receive frequency. Are they the same? Nope. And that's where that frequency diversity comes into play. So you got one that's transmitting, the other one is receiving. So we can go back to that frequency diversity that was covered. How about polarization diversity? The reason why you set your transmit frequency with the polarization is because the other side is transmitting at the opposite polarization. So in other words, if I'm vertical, the other side's got to be horizontal so they don't interfere with each other. And also, if you hadn't noticed, if you take a look at the distant end, their frequencies are always flipped from what you have. So that's what that filter's there for, in order to weed out all the others, but at the same time, I gave you a little bit extra on the why you need to set 2 frequencies and not 1, going back to polarization diversity, as well as boom, boom, boom. There you go. Sergeant McCusker wrote it in. It's on your tech order. So hopefully that will explain why you have to have your filter set, or what it is set to. Nice going there, Sergeant McCusker.
You got it there.
Any other questions? DSU and CSU. Oh boy, gotta love that one. And I got the for you, buddy. I had just looked that up. No, I'll do this. Let me go back here. There is an image that explains this the best. CSU and PSU. Fat fingers. Ah, crap. I really fat fingered that one. Let's go to images. Let me see if I can find it. All right, can everybody see the image that I've got up?
Looks good.
All right. So the CSU DSU is here, and the CSU DSU is here. Okay, which one of these, and I'm not going to answer the question until somebody types it in or answers it over line, which one of these is for the user, and which one of it is for basically the server area, or mainframes, whatever you want to call it? Is CSU for the user. So in other words, if the user is here, that means the DSU is here, right? No, actually, I think the DSU is for here. Yeah, DSU is for here and CSU is here. CSU does not mean for user, customer. Nope. CSU is actually for the mainframe. DSU is for the user. Did you look it up in your study guide workbook there? It'll tell you. You look it up there, Sergeant Meeks? Prove me wrong.
So is the CSU on the inside of the network where the DSU is on the outside of the network or outside of the router?
Okay, hang on just a minute. Sergeant Meeks is saying, I did before. Now you're going to make me pull up mine. Go to my study guide workbook. Where's the CSU, DSU, Sergeant Meeks? One Charlie, okay. Empty Arms Hotel. Here comes the dogs barking. Got a page? Page 33. Thank you. Okay. Yep. Good point, Sergeant McCusker. They're in the same box. AT&T uses them a lot. So if you read what Sergeant McCusker is going over, the DSU and the CSU are normally in the same box right here, with the DSU here and the CSU here. So when you get online with AT&T, you know, the first thing they want to do is they want to see whether or not they can shoot a line back at you guys, you know, the customer, and that's where the DSU comes in. The CSU is actually in between the servers. So if everything is good between where they're at and to your service, and they can't find anything, then they're going to go look at the other side. So that's what they do, and that's how they use it in the network. There was a better one too out there. That one's in Japanese. I don't think I can use that one. So what's a DTE? Okay. What's DCE? Okay. So just always remember that T is for terminal, which means your computer. Let's see if that's a better one. Nope. So what are the three things that the BERT does for us? Good point, Sergeant McCusker. Everybody knows the BERTs, bit error rate test. Now, better known as the, what is that, the HST 3000? So what's it used as? And if you did the NSM lab, it was used in 2 different ways. Could. In other words, you're using it as a monitor to see what errors it has. I'm trying to find out if we have anything else here that I can give you. Ah, here we go. Does that explain it? Take a look at the diagram I have up here. So DSU is on the customer side, CSU is on the other side. I'm saving that one. Copying that bad boy for later use. Come on. CSU. I knew that there was something else in there. Okay. Any other questions? Ah, good point. So why is there a gap between the RF assembly and the baseband assembly? Well, there's that 150-foot cable, right? Have you ever thought about, well, gee, I have a hut here, and I don't want to go outside and monitor it. It's less than 100 feet. Wouldn't it be easier if I just set the RF module out there and then bring that 150 feet in there, and I can listen to it on my baseband assembly and connect my multiplexer up to it? I'd want to stay in out of the ring, wouldn't you? That's what that 150 foot is used for. Is, you know, if you're on top of a mountaintop using it as a repeater, that's one thing. But if you've got like a tent with some multiplexers and you need to run it out to the baseband assembly, but it's, you know, wouldn't it be easier just to troubleshoot your multiplexer with the baseband assembly to see if everything's working? I like to stay in out of the rain. Maybe it's air conditioned. Just a thought. Maybe it's heated. Good point too. It's a safety issue too. So if you're really close to the baseband assembly and you get a bomb dropped on you. Remember now, the enemy is always looking for your comm. Yeah, this is very true. It does make sense. So you can do 2 different things. If you're running a repeater, you got to have 2 of those together. So it doesn't make any sense to separate the baseband and the RF assembly, and then another baseband and RF assembly, and run the baseband somewhere else. It just doesn't make any sense. So if you're on top of a mountaintop, yeah, you would want those 2 together. It would not make any sense of that. But if you're, you know, in a comm area, setting your antenna out at a distance is so much more easier. That's the reason why when we do CTMs and that we want to have a longer cable to bring back into the tent. Remember now, the enemy's wanting to kill you. It's easier to replace a mask than it is a physical human being. Oh yeah, what is the maximum repeaters for the TISR? Anybody know? Anybody? 7? How did you come up with that number there, Airman Sanger? Well, it's an educated guess. Now put some logic to that number. What did you learn about repeaters? Okay, good. FDM is 8, TDM is 15. What does this use? Baseband. Yeah, good point on that one too. So you're looking at FDM, TDM with the Tisser, and this is my experience now. We've been able to do this using a repeater. It's going to break it down into baseband. Baseband is not IF, so it's one step below there. So you could actually say it's TDM. Because all you're doing is once you come out of it, you're going to a multiplexer, not baseband. Actually, yeah, it is baseband. So you're going to a multiplexer, so you could actually connect it up, pull traffic on it, so it would be the third one. 15 is my guess. But why in the world would you do 15? Wouldn't you want to find a better piece of equipment to go farther? Of course, then again, if you've got 15 tissers, you're better than most other people. Normally have between 2 and 4. What's the max distance for a tisser? That's good, but it's wrong. You know how I know it's wrong? If you take a look at your tech order, it has that little sign in front of it called less than 25 miles. So that's with the 2-foot dish. With the 1-foot dish, it's less than 10 miles. So please look at the sign. Okay, keep going. Any other questions out there? Hierarchy, oh boy. Talking about TDM hierarchy, correct? Okay. And that's the bad part about this mouse. What the heck? I just downloaded it. Well, when everything else fails, go to your Google it. And I probably misspelled that like crazy. Okay, you see that diagram? And that's about as good as you're going to get it. So the first one here, you'll see that it says DSO. That's a 64K channel. So you got 24 of these going into TDM, and with that all in mind, it ends up becoming a DS1. So that's approximately well, I shouldn't say approximately, it's 1.544 the way that math all comes together. So 24 channels at 64K, add another 8,000 I think to it, and you get 1.544. So that's coming out of one TDM. Add 4 of these TDMs, multiplexers, going into another one, and when they combine all of those together, you get what's called a DS2, which ends up at 0.312 megabits per second. And there are, when you come into this next TDM, so it goes 24 channels, 4 multiplexers, 1, 2, 3, 4, 5, 6, 7 more to get a DS3 at 44.376. And then in order to get a DS4, 1, 2, 3, 4, 5, 6 of these to get your DS4 coming out. That's what that hierarchy means. I wouldn't go there, just to understand what hierarchy is. Just remember you're combining multiplexers. Remember now it's about basic facts about TDM. We're not going to have you memorize every freaking number, because if that was the case, we would have you memorize the tech word, right? Yeah, good point, Sergeant McCusker. Any other questions out there? Hopefully I got everything taken care of. So now's the time to ask, please. Don't be afraid to ask.
With one for you.
Sure. I got all day. Well, at least until, yeah, 4 or 5, I don't know. Questions, gentlemen? And if there's any ladies out there, now's the time to ask them. Test is too late. Unless you guys want to take a break and then come back a little later. You're welcome. You are very welcome.
All right, sir. I have nothing for myself. I'm good to go right now. Thank you.
Okay. Here's what I'm going to tell you. All right. If you are having some issues, and I am on Discord most of the time, and the reason I say that is I play World of Tanks and, you know, whatever. And you really need some help, I'll try to help you out, okay? So just send me a message. I'll get to it. It'll pop up somewhere, and I'll get to it. Any
Really
other questions?
appreciate that.
Not a problem. Not a problem. That's what I'm here for. Any other questions out there? I didn't ask Sergeant McCormick. Way to go.
Yeah, same goes for me. If anybody else has questions, I'm also available.
Yeah. I mean, it's easier if you do it on Discord, and as we're, you know, getting on and off, it's so much easier all the way around to see that little pop up because we can see the top in our chat line. So, you know, we may or may not get to it right away. So, you know, and no problem there. We just ask that if you've got an issue, and let's say it's, you know, over the weekend, just do a quick chat, and we'll probably get back to you, set up a time that we can coordinate and go from there. Whether it's a video chat or just, you know, like we're doing now, the live stream. And if anybody else has any issues, I'm sure any of the other instructors will try to help you out too.
Thanks, Mr. Mayor. This was awesome.
Yeah,
I know you still have an echo, so I'll figure that one out. Remember now, this is our very first time. This is new to me, talking at this little thing. I got a new camera. Oh, good grief. I did define my device. Anyway, any other questions out there, ladies and gentlemen, before we sign off? Okay, good point. Sergeant McCormick, please send me that so I can edit it and we can put it on. Everybody knows about RF Transmissions YouTube video. We'll put it out there. Give me a day or two to edit it, and I'll post it. Now, I'll put it on the chat in 20014? Yeah. I'll put it in the chat for you guys.